So here we are picking up the lecture again. We're going to be a little bit more deliberate, talking about how to find the value of this improper integral. And again, it's improper because it's got that infinity as one of the limits of integration. Our automatic step is to take the improper integral and to rewrite the improper integral as the limit as b approaches infinity less u of e to the x, or x times e to the negative x dx. Now, yesterday when we were screaming through this, I quickly did the tabular integration for this. I wrote down as side work something real quick. Quickly, I wrote down x and e to the negative x, and then I did a chain of derivatives. Derivative of x is 1, derivative of 1 is 0. That's where I can stop that line. And for everything in this one column, I'm going to do integrations of e to the negative x. Negative e to the negative x, and then the antiderivative of this is e to the negative x. And then the tabular integration method says I'm going to throw a plus sign in front of these two terms. I'm going to throw a negative sign in front of these two terms. So I end up with negative x times e to the negative x minus e to the negative x plus c. And that's the antiderivative of that. If you don't remember that method, please recall we could have also said that u is equal to x and dv is equal to e to the negative x dx. du is equal to dx, and v is equal to negative e to the negative x, and that then the integral of x e to the negative x dx is equal to u times v minus the integral of v du. And you can see that these things end up having the same answer. So regardless of whether we do tabular integration or the more explicit integration by parts, we come back here with our next step, which is that the limit as b approaches infinity of negative x e to the negative x minus e to the negative x as evaluated from 1 to b. And then we're going to evaluate this expression on these limits of integration. The limit as b approaches infinity of negative b e to the negative b minus e to the negative b, there's our upper end, minus e to the negative 1 minus e to the negative 1. With all those plus signs, this looks like it's going to be 2e to the negative 1 down here. But what do we have going on here? Well, as b goes to infinity, negative e to the negative b, that's going to be e to a really big negative power. It's correct. Sorry. Not okay. 0. All right? So when I apply this limit to here, that's going to be a 0. But what happens when I apply this limit to there? I've got infinity times 0. Is it? The answer is sometimes. 0 times infinity is Indeterminate. And if it's indeterminate, our best tool is L'Hopital. So let's, everyone saw me erase that successfully. All right.
Mr. Figueroa, before we continue, why did the sign change in front of the E?
Here and here, because I had a negative sign here as well,
Oh.
and I distributed that negative through. All right, so what is the limit as b approaches infinity of, we'll just do the positive version of this, b times e to the negative b. Indeterminate in the form of 0 times infinity. So let's rewrite this as e to the negative b over 1 over b. Oh,
Could we just do it as,
how about b to the negative 1?
could we just do it as E to the B?
Is that okay? b is going to infinity and now the bottom is going to infinity? Edmund, you're a genius. That's a lot easier than what I wrote.
Yeah, that's what I was supposed to say.
Well, good. Keep me from doing silly things like that. So this is now indeterminate in the form of infinity over infinity. We came up with a new word earlier today at Berkeley High School. It's L'Hopitalable. Okay, it was much funnier this morning. Is L'Hopitalable because it's in the form of infinity over infinity or 0 over 0. So go ahead, let's take the derivative of top and bottom. And we get 1 over e to the b. And what happens when I apply the limit now?
It's 0.
I get 0. So this ends up being a 0 as well when we apply all those limits. And our ending answer is 2 over e. Hey, that limit exists. Because the limit exists, we say that the integral that it came from converges. So they just want to know, does it converge or diverge? Oh, sorry, evaluate it, it's equal to that, and it's convergent. If we ended up not getting a limit that made sense, then we would have said it divergent. All right, so there's the, yes?
Once you have the 0 there, then how did you bring it back?
Well, this part right here is essentially that part right there.
Yeah.
B to the, so I replaced this with that 0.
So the limit applies to every piece of the.
It applies to every piece, all 4 of these pieces. But I could, these are constants, so it's not going to affect those. So I just put it where the b, I took the limits where the b's were. Long pause.
I'm wondering how long it would have kept going if we would have kept it like e to the negative b over b.
No, it's still, no, it would have been bad. No, it would have been bad because if we would have took the derivative of that, we're going to get b to the negative 2, and then b to the negative 3. And soon enough I would say, wait a second, this is going the wrong direction. So I would have done it no more than 4 or 5 times. before I realized it. Are you ready for a new problem?
Yes.
Here's a new problem. Okay, in pairs, please.
Okay, so we just goes up to the two things because of our infinity.
Yeah, so this is equal to
Okay, so now
negative infinity to.
yeah, so it's like looking on the board.
Well,
Oh wait,
That was
Get
the,
the automatic stuff done?
that was the example that he just.
Give me those 2 automatic steps, please.
Because that way you can just, because the zero doesn't have anything, and it's just, it's kind of like a,
And then don't you have to get rid of it?
yeah, you get rid of the negative infinity by putting the variable in, but first you gotta split it, so. Apart the. Yeah, now you do that. So now it's a to 0 dx.
And now we
Yep.
have to take the x.
B.
So,
Well,
yeah, that's what we did on the
Yeah.
specific design. And
oh, and then of course you have the limit of such.
the interval.
The limit as a approaches negative infinity.
One plus x squared, and then bring x squared out and put the root of it. I'm gonna do 2.
And then you just evaluate it for
So
that
the
specific.
2x on equals x.
This one.
Everyone should have this written on their paper by now, right?
Yep. And that's why we can see, if you remember, this is pretty much
Yeah.
1 plus x squared. And 1 plus x squared is a specific,
Okay, so good. I want to try to get it.
tangent
Evan, you amaze me.
Tangent.
Oh, yeah, that's like so good.
Yeah, so the derivative of this is tangent. So limit as a approaches as
Evan, since you said it, can I put it in the thing?
Yes.
Edmund has a hint for you.
Oh, it's the,
Well, wait, so do you not say limit anymore?
No, see that's what I
You,
did?
you knew that. You knew that.
Wait, do you not say limit anymore when you use it in my head?
No, I'm just, no,
Just giving them a hint.
Oh, you're
It's-
just saying.
I'm giving you the hint that once you get to this part, the next step is going to be to do that antiderivative. And that antiderivative, with the limit name in front of it, is going to be
So at this point,
inverse tangent of x as evaluated from a to 0.
so at this point, so now,
T looks like an F. Just saying. Right there.
so now we have,
The inverse fan. That's the fan that blows things away from it.
So get rid of our integral sign, so now we gotta add a little. Okay.
I don't think so. So it's between what and what?
Yeah.
That's not, no. Well, it's, what is that number? Huh? Like pi over 2?
Yes.
Yes, it is.
Pretend that we didn't know it was.
It is.
Okay.
Oh, yeah, no, because
Well, yeah, yeah.
normal
it's-
convention.
Yeah. So,
Why does, yeah, why does that count?
alright, so,
So we have, so A is
So,
negative pi over
yeah.
2 and B is
yeah,
pi
so,
over 2.
0 of tangent x is 0 minus as a approaches negative infinity.
That's where I got.
Wait,
So
are
that
you
doesn't
saying
work.
the inverse tangent of
That
pi
thing keeps you from doing
negative pi
that.
over 2 is 0?
Yes.
You want to change this into a 1 over u. Well, that means that's equal to u. But then you have that 2x thing that's it's not the 2, it's the x part that keeps you from doing that substitution. So that's the reason why, that's why a natural log thing doesn't. And by the way, neither does integration partial fraction. You can't do partial fraction on that either because 1 plus x squared does that factor. Sorry, it doesn't factor in the reals.
No, because tangent inverse.
So both of those are pretty good ideas.
So it's negative inverse tangent.
Minus.
Okay, we're gonna stop for a second.
Oh, yeah.
You make this.
I made a drawing on the board, and I want to know what does that drawing have to do with our problem. Nicole?
Isn't it like that, or A and B equal, or the S and B
I would say what A and B are equaling can be represented in this graph. B is this value here, and it's getting bigger because it's approaching infinity. I would say A is down here, and it's going to the left, and it's getting smaller. So I'd say A and B are represented in those graphs and those ideas of A and B being upper bounds to the area under a curve. Anything else about this graph that would allow you to stop right now and not have to do another step? Ryan?
It looks equal on both sides.
It does look equal on both sides. And now comes in one of the unfortunate things about this kind of section. I want to say that the positive stuff here, which is the area under the curve of under the inverse tangent curve, would get canceled out with the negative area on that side. That's what I want to say.
It does.
And the answer is it doesn't.
Doesn't.
We have a rule. We've got lots of rules. But here's the rule that is in play right now. Ready? I'll do it in red.
Must be like problem over.
In order for the integral from negative infinity to infinity to converge, both the integral from 0 to infinity and the integral from negative infinity to 0 must converge. In order for the overall integral that we broke into two pieces to be convergent, both sub-integrals must be convergent. Now, I ask you this question. Is this integral, or is this limit convergent based on the drawing of the inverse tangent curve? Is there a finite amount of area under this curve as b goes to infinity? Every time I take my b out, that area gets bigger. It is an infinite amount of area. If that's true, this limit does not exist. And therefore, this integral okay. That integral diverges. Okay. So Edmund, I know what you're thinking, and I wish it was that way, because that makes perfect sense to me. But the rules that they've set up for us say both sides need to be convergent, even though it looks like yin and yang. One cancels out the other.
Well, it's not so much that it cancels. If you put tangent inverse x into the calculator, and then you put in an extremely large and an extremely negative number,
You should get something that's extremely
yeah,
close to pi over 2.
Yeah.
Negative pi over 2.
Yes.
Okay, so this is down here, this is negative pi over 2. Here's pi over 2. Yep.
Isn't that,
And inverse tan has asymptotic behavior to those two vertical asymptotes.
right,
Sorry, horizontal asymptotes.
right, so as it approaches infinity, that value is getting closer to pi over, well, at least on the,
But the integrals is talking about the area under the curve. And that area is never going to be finite. That area is infinite. You remember how we started this lecture? We started with this curve. And we talked about this curve having a finite amount of area even as b took off to infinity. This curve, as b goes to infinity, has an infinite amount of area. It does not converge to any particular value. Instead, the area under this curve diverges.
I don't understand how the one up there has finite.
Neither of these have finite area.
Okay.
All of these little limits don't exist.
But the one you started at around the side.
This was the one that we started with on the very first slide of the lecture.
Was it different?
Well, it was a different curve. It was like e to the negative x over 2.
Yeah, but when you keep expanding that value, it's gonna keep getting.
Well, at the very least, this curve had asymptotic behavior to the x-axis.
That one has.
No, this is the x-axis right here.
So why does it have to be to the x-axis if it's like, if it's not gonna go beyond pi over 2 and the y?
Because we were always measuring the area between the curve and the x-axis. This area between the curve and the x-axis is always big. As b gets bigger and bigger, that height keeps on getting closer and closer to pi over 2. It always has height.
Isn't that-
This one, as we get closer and closer, as b gets closer and closer to infinity, the height's going away.
But it's still always there, isn't it?
Well, that's seemingly the thing that blows my mind too. It always has at least a little bit of infinitesimal height, but still it has a finite.
So it doesn't really matter then if it's really tiny.
Well, I can tell you right now, unless the curve goes towards 0, it's gonna be divergent.
So basically.
so is that the
saying
rule
if
we
the
can
curve-
follow?
Wait, 1 second, go ahead, Candace.
So if the curve never touches or goes anywhere close to 0, it's just divergent.
Okay, I like the way you said that because it's exactly right. If the curve goes anywhere else besides 0, it's going to be divergent. Okay, now the thin ice we have to walk in. Ready? Is no, actually at this point I think actually this drawing is sufficient proof to say this is divergent. Really, but I want to get back to a problem that we did. This one. Do you remember the conclusion here?
Divergent
This one was divergent.
to
Even though this curve approached 0. So, now I want to make sure, because Candace, you said it perfectly. If it's going someplace other than 0, it's going to be divergent. Perfectly said. If it goes to 0, it may or may not be convergent. Now the good news is, by the second the second section of chapter 9, we will have nailed a way of observing which ones that go to 0 are convergent and which ones are not. So, goes someplace other than 0, divergent. If it goes to 0, we have to check by actually do the integrals. Can we live in that space for a little bit? Yes.
Yeah, it's still like basic, but I'm having a hard time. You say it's like convergent, are you meaning that like the lines are like meeting at a point? I don't know, I can't.
Okay. Let me see if I can address that question by going back to the original problem that we started this section with. All right? This curve, and then we had said, what's what's the area between 0 and b? And we got an expression. And then we said, what if b goes to infinity? And we found that the integral from 0 to infinity of this curve was equal to 2. What does that mean? That means if you tell me how close I need to get to 2, I should be able to figure out how big does b have to be to get close enough to 2. I never reach 2. But if we say as b approaches infinity, this value approaches 2, it's a matter of saying, you say how close, a billionth, I say how far down the line we have to do to get within 1/1000th of being, 1/1000th of 2. Alright? That's the nature of these limits as something approaches infinity. You tell me how close, I tell you how far. Alright? Anthony, you had your hand up.
Oh, why did you draw that graph for d of x over it?
I drew this graph to go along with this one because this was an example of a convergent integral.
I'm talking about the other one.
This one,
Yeah.
this one is y is equal to 1 over x. It looks almost identical to this one, but the area under this curve is divergent. Meaning there's no particular value that it comes close to. In other words, another way of saying this is, if it's divergent, you say, when does the area under this curve get to be bigger than 10? And then I tell you how big of a b you have to go to get bigger than 10. There's no upper bound to the area under this curve. There is an upper bound to the area under this curve. That's why we classify the area under this curve as being convergent, while the area under the curve 1 over x is divergent.
Wait, is it because it
So the
crosses
number
the
would be,
y-axis?
like your b would be how far you have to go to get to 10?
If you said, if I say it's divergent, you say, well, if it's divergent, there's no limit to the area under this curve, how far to get to 10? And then I would say something like, what was this integral? From 0 to infinity of 1 over x, change that to a b. Natural log of x from 1 to b. So I say natural log of b minus the natural log of 1. And you want it to be 10? Okay, I'm going to solve this equation for b. How big?
So it would just be your b, is how far to go.
Right. This area is unbounded. You tell me, no matter what number you put here, I can tell you how far we can go to get that number. For this curve, the one that was convergent, it's going to 2. That area is bounded by the value 2.
It's never going to be more than 2, but if I give you the area,
If you get,
if you say what you need to bound it at,
if you say it's 2, you can say, how far do you have to go to be within 1/100th of that value? And then I can give you a value b that gets me that close. And if you say, no, what about getting within 1/1000th of 2? I can give you another b further out that gets me that close. No matter how close you tell me on the bounded version, how close, I can tell you how far. So I'm bounded, how close do you want me to be for 2? For the unbounded, how much bigger do you want me to get it to be?
so that's what we're doing in this section is finding b.
No. Why are we doing this section? We're doing this section because we have to look into the nature of adding up an infinite number of things and getting either a finite or a bounded or unbounded value. Can I give you just a sneak peek into chapter 9?
Yeah, 'cause I have no idea what we're doing.
Oh, plus 1/6. Plus 1/6.
infinite number of non-zero fractions here and add them up.
So finding the integral is like adding them all up.
Bingo! Bingo!
Isn't that what we were doing with the volumes and all the little things? We're adding them all up?
Bingo. So integrals are adding up like a bunch of little things. In chapter 9, we look at what happens when we add other things up and whether the behavior of that infinite sum of numbers is bounded or unbounded, convergent or divergent.
And
All right.
it's conversion if it's
This
bounded.
particular series, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, so on and so forth, it is convergent, and it converges to the value 2.
So what you're finding?
So, I know this is really, really tough, but ready? I'm not caring much about whether I find anything. I simply want to start classifying these things into two groups, divergent and convergent. All right? And that's my biggest worry, or my biggest issue right now. Can we get a feeling of what it means for an integral to be convergent or an integral to be divergent? This feels like a very different kind of calculus, because I'm not caring what the number answer is. I'm caring more about classifying it into these two groups. Cole?
So I still don't really understand, like, when you say, like, this one is bounded by a 2, and then that one's not, like, how did you know that, like, just because it was given, that, like,
No,
it was
we calculated both of these, Nicole.
Oh, so it was just when you calculate it?
When I calculated the limit as b approaches infinity
Right,
of the integral from 0 to b of e to the negative, when we calculated this, we got the number 2.
okay, so the limit you guys, like, with, okay.
So the limit we got ended up being a finite value. And then we classified this integral then as convergent. This, let me write this out more clearly. The limit as b approaches infinity of the integral from 1 to b of 1 over x dx. We calculated this. And after we did the antiderivative and applied the limits of integration and then applied the limit, we got infinity. We classified this integral then as divergent.
You can't really just, like, look at a graph and know it, well, not.
Well, Candace came up with a really good rule. Candace's rule
Well, yeah, that's 0.
was this particular graph is going to be divergent. Because as b moves closer and closer to infinity, there is always more area that's being added on. Well said. Things that look like this may or may not be convergent, depending on what we're going to find out, how quickly they go towards 0. And we're going to give a lot more information and more details we get into chapter 9 about that. Candace, and then Emily.
Something I noticed when you said, the ones that are approaching 0 that were divergent, the ones who were convergent. The ones that were convergent crossed like the y-axis or like this touched each other. But the one that you said was divergent didn't necessarily touch each other. So I was wondering
Okay. Here's what I'm hearing. Ready? You're looking for clues that's going to help us. No, this is what humans do. Humans take data from their senses and then they try to make sense of it. That's why they're called our senses. No, I mean it's true. We are machines that try to imply meaning onto the things that we see. Right? I would say what you saw was indeed a relationship. Unfortunately, I'll tell you right now, it's not the relationship that actually ends up bearing fruit. You want to know what the thing is?
Yes.
Ready? here's the one and only thing I look at when I'm trying to look at, say, is something convergent or is something divergent? Oh, let's say from A to infinity, because I don't know. That is divergent. That is convergent. There's a boundary. And that boundary happens to be at 1 over x. If you get a power just a little bit bigger than that, it's just enough to make it divergent. There's a boundary. Remember, all that time that we looked at is, what, does so-and-so go faster than so-and-so?
Yeah, that's
Know what that means?
oh,
That's divergent. Why? Because this grows faster than that. Anything faster than 1.1 or 1.01 or 1.00001, anything faster than e to the power of 1 ends up being divergent. We're going to see that more in detail 9. Can you wait until 9 before I can really flesh that all out? Okay, but we're laying all that groundwork in section 3 and 4 of this chapter. Yeah.
So when you found, as long as you know it's divergent if the limit equals infinity or what else? 0?
Say that one more time.
Well, we said we knew it was divergent because the limit equaled infinity.
Because the limit equals infinity, right?
Yeah. Is it 0 as well, or just?
If the integral equals some finite value, then the integral itself is convergent.
And 0 is considered a finite.
Yeah.
Okay.
All right. We've got to. We did that one. We did that one. We did that one. Okay.
what if we
Besides limits of integration that have infinities on them, there are other improper integrals as well. They happen when we have discontinuities associated with the function that we're taking the integral of. So, for example, well, first of all, you might want to write them in your notes, and then I'll parse this through. Okay? Well, I noticed a contradiction in something I said. What? I noticed a contradiction in what I said, and I'm like, that bothers me. I'm going to look this up, this example that I took from your book. After you write this down, I'm going to try to salvage the previous line. I screwed up. It happened. Well, in fact, you know what? Excuse me. Can we go back to the slide, please? Here, all right. Sorry. Can we go back to this one, please?
Does it convert? Because
confused.
Okay, I made a mistake. Okay, and the mistake I made was, I don't know why I mixed two ideas up, but here's the idea. Do you remember I just said a second ago, if the thing in the denominator was like greater than the power of 1? So wouldn't, by that description, wouldn't this be a convergent series? Yes, it would. So what's going on with this inverse tangent thing? This is the thing, I'm so sorry, Evan. You were trying to tell me the whole time. You were trying to tell me
That's
the
what I was saying. Like,
whole time.
he kept saying it. I was like, yeah, all right.
Come on, erase. All right.
So our rules no longer apply?
No, no. It's almost everything else that I said was right.
No, but what about the curve out if it goes to 0?
Because you know what? Do you know what this curve looks like?
Not like that.
It looks like this. Oh. It looks like this. As x gets bigger, this approaches 0. Okay? There wasn't a contradiction here. What Edmund kept on trying to tell me, and I was too wrapped up in my own fascination with my intelligence. Okay, let's just take that part. Yes, it is true that inverse tangent looks like this. And indeed, while a approaches infinity, inverse tangent looks like it approaches negative pi over 2. This part is tangent, inverse tangent of 0, which is 0, plus pi over 2. It is pi over 2.
Well, yeah.
Okay?
Wait a minute. That's, I got it.
Yeah.
Wait, do I have it wrong?
No, you're
That's
just
right.
doing that one.
I'm just doing that one.
Yes.
Wait, why isn't it negative?
You could try the double.
No, but the area, no, because the area of the original curve is above the x-axis. It's fine. It's fine.
Yeah.
All right. So this part, this limit does exist. It is a finite value. This part of the integral is convergent. And if we do this one, the limit as b approaches infinity of inverse tangent of b minus inverse tangent of 0, and as b approaches infinity, inverse tangent approaches pi over 2. This one goes to 0, and so we end up getting the sum of those two. We end up getting pi. This curve does approach 0, and I kept on confusing the original curve, the one that's in this problem. I kept on confusing it with the curve of the antiderivative, which has an unbounded area under it. What happened is in the middle of this problem, I started doing this problem. Ready?
Tangent inverse.
I started doing that problem, and that's what got muddled up. This problem
So does that
Divergent.
is divergent. This problem
Because the graph that he drew that it
is convergent.
that's not the graph of this.
Oh my goodness gracious! I went off. Oh,
The graph of this.
we're never gonna get those 15 minutes back either. Oh, okay.
when you had 0 minus 1 times pi over 2, you ignore the negative.
I was trying to be really careful.
Weird.
Over in your circle box part,
No,
like,
'cause I got it.
I was
I was like,
you had 0 minus 1.
Well, this is inverse tangent of 0, which is 0, minus.
it's really wrong.
Okay, and inverse tangent approaches negative pi over 2, minus a negative pi over 2.
Oh, that was negative, you crossed them out.
And I,
Got it.
okay. All right.
It's not going to make any sense to you in my opinion.
So does anyone see like that one point where I'm going, wait a second, that doesn't make any sense?
Yeah.
Because I said 1 over x squared is convergent. Guess what? 1 over x squared and 1 over 1 plus x squared are essentially the same curve. They grow at the same rate.
Yeah, they're all the same. Wait,
And guess what? Things that grow at the same rate are either both convergent or both divergent. All right.
So, we may not have.
Okay. That's where we are. We got less than 3 minutes. I don't think we're gonna be able to do much damage to this particular topic. Okay. So here's where we're at. Today's Wednesday. Tomorrow is Thursday.
And Friday.
But the test has been scheduled for Monday. Okay, so even though I didn't get through this doesn't put us off schedule. We're still scheduled for a Monday test. All right, I can tell you that you may do quite a bit of damage on this 8.4 assignment, even though we didn't get to the very last part.
No, CJ's a bad liar because he just sounds sarcastic when he says
Mr. Fedor, what's the